I'm gonna talk about possibilities for cluster algebras. I write it small and I speak it small because this is a conference representation of algebras. But I will never use algebra. In my talk, there is no algebra, there is no representation, there is no mononomial. What I mean by algebra is high-square algebra. Not really algebra. Okay, so history part. History part. Okay. So it starts in physics. In 1994 or even earlier, Cyborg developed the duality for fibers. Here, fiber. So in my talk, fiber would be just a directed graph, but I allow multiple arrows. But I don't allow loops and oriented cycles of length. Okay, so what is the Cyborg duality? So suppose that my fiber has oriented path like this locally, and then if I apply a Cyborg duality at J, then it's just the composite of two oriented arrows will become a single arrow from I to K, and then the arrows incident with J will be reversed. It's called Cyborg duality. And if this is a nice duality, then the dual of dual will be original. So if we take the dual from here, then I will get there is old oriented arrow from I to K already. Since I'm taking the Cyborg duality, I will create arrow from K to I, and then the arrows will be reversed at J. And since I want these two to be the same, I will cancel two cycles. So that's why I don't allow two cycles. Actually, in string theory, two cycles do not contribute to supersymmetry, so that's why we cancel two cycles. And the reason that the string theorists developed this duality was that I'll not go into the detail, but under this duality, certain moduli space of fiber representation. Preserved under this view. So what string theory usually does is they want to compute, for example, the Euler characteristics of moduli space of fiber representations. Since these moduli stay the same under duality, if you have a complicated fiber, they apply Cyborg duality, keep applying Cyborg duality until they get a simplest one. And then it would be easier to calculate the Euler characteristics of modular fiber representations. Anyway, that was history from physical side. Matters of on mathematical I'm not sure Fongin and Zelensky already are aware of these things. Probably not, from what I heard from Zelensky. But anyway, they accidentally found the same thing, and they found more things in there. So from what I heard from Zelensky, he was playing with some computations for total positivity and quantum groups, and then he found some interesting Laurent phenomena, and then to make Laurent phenomena work, he has to have this kind of Pivot mutations. So anyway, they discovered the algebraic structure on this type of duality. So what are these structures? So if we have, so suppose that I have the same figure, and then of course on the figure side I will have the mutation. Now I will call it a mutation instead of duality. On the figure side, it's just the same. But what they do is they attach certain functions to each vertex. And then they give a rule for the transformation of these functions so that they work very nicely. So these are rational functions of x1. I could have more than 46 many variables, but anyway, I don't care. So even if you are an expert in cluster algebras, what I'm going to write is different from the standard definition. So if I have a figure, I will assign a set of variables, and also I will assign a set of functions of those variables. So I need two data. And then if I apply the mutation, if you are an expert in cluster algebra, you would say that it becomes like fj. So this one becomes the denominator, and then the numerator has the binomial. One is from incoming arrows, and the other term is coming from outgoing arrows. But I'm not going to do that. So my definition would be like this. This would be a still rational function, but not of the old rational, of the old variables. I will introduce new variables. X1 prime, X2 prime. So what I mean by this is I replace x1 in each function, every x1 in each function with the x1 prime, and x2 with x2 prime and so on. So all rational functions will be changed in terms of new variables. But of course they are related. The old variables and new variables are related by the following rule. Old variables and new variables are almost the same, except for one variable. So I'm giving a little weird definition. This cannot give a, so I cannot define a cluster algebra from here. So that's why I'm not talking about algebras anyway. So I just talk about cluster variables. can I erase? So if you are an expert in cluster algebras, normally what we usually do is we start with the initial seed, initial cluster, and keep mutating, and we get a terminal seed, then terminal cluster variables in terminal cluster will be expressed in terms of all the initial cluster variables, but this is different. We start with the terminal seed, terminal cluster, and then keep mutating to initial ones, and still the expression would be terminal cluster would be expressed in terms of initial cluster. But so basically, we are going backward. Okay, so of course we can take an arbitrary sequence of mutations. So in general, okay, for simplicity, let's say I have a finite quiver. It doesn't really matter. It could be an infinite quiver, but for simplicity, let's just keep it finite. So my notation would be complicated because I always need two data, variables and functions. So I keep track of the set of variables, and also, so I could mutate in any direction. And I can. Quiver will be transformed, and then also these functions will be transformed. So I keep mutating. Okay, so for those who are not familiar with cluster algebras, I'll give a definition for cluster variables. So, pair of quiver and a collection of rational functions is called a seed. And the elements in the sequence, in this cluster, are called cluster variables. It's just a name. They are not necessarily generators for certain algebras, because I'm not talking about algebras. Let me give an example to show that how this rational function can be complicated. When we have two vertices, there are not many choices. The quiver has just two vertices, and since we don't allow two cycles, but we allow multiple arrows, so we have all arrows are in the same direction. This direction or opposite direction. And then if we have two vertices, cyborg duality is boring. We just reverse the arrows. So on the keyboard side, the keyboard mutation side, it's not really interesting. But what is interesting is on the cluster side. I could either mutate at 1 or 2. Let's start at 1. Keywords are just taking opposite keyword and then opposite, and then it's not really, there's nothing new. Now I'm substituting xi semicolon, my notation was too small. So these are variables at the seed 1 will be substituted by new variables. So that would be x2. Now my second seed, the second index would be 2. Since there are r outgoing arrows, I have r power of the variables pointing at, and then there is no incoming arrow, so 0 to power is conventionally is equal to 1. It doesn't look different from the standard way, but it will be different. If you take one more mutation. Keyboard is just the opposite of opposite. It's what we started with. So So I need to replace every variable. Right. So especially x1 2 will be just x1 3. That's good. But I need to replace x2 2 with a rational function, Surton rational function. So it will be like this. Again, there are just r outgoing arrows. Either r outgoing arrows or r incoming arrows. 1, 3. So every rational function will be changing. So actually, that means this is a rational function of the variables at seed 3, and also this one is another rational function. And then after, so you can keep doing this. So if you apply one more mutation, then you will get like three times of power. So it gets very complicated. R, something R, some R. And then the denominator will be no longer a monomial. Denominator also has something. So as you mutate further away, more and more, this gets very complicated very quickly. I think it's like it grows like a double exponentially. So the expression will be very complicated, but it does not mean that it's out of control. Actually, we have control. We have to have a full control over these expressions to get a positive. For those who have not seen cluster algebras before, if the simplest interesting case is when R is 1, and I still have two vertices, then these complicated looking rational function will become So as I promised, I'm doing high school algebra. So it will become compute to simplify factor, then you get going in general for any keyword, for any mutation. In general, there will be miraculous factorization first, and then miraculous cancellation. They occur for every mutation sequence, for every keyword. And even if you factor the quotient, both factors would have still positive coefficients. I mean, that's what we need to show. Okay. So when Zelensky played with total positivity, he discovered this cancellation property, and then he was amazed by and forming generalized. So after cancellation, after factorization and cancellation, our denominator will be always just a one-term monomial, so it will become a Laurent polynomial. Of the variables at seed t, when we say variables, we have to specify the seed. Of course, they looked at these Laurent expressions, and then they observed that it looks like they always have positive coefficients, so they made it as a conjecture. So basically we are dividing a positive polynomial by another positive polynomial. So, but the resulting quotient may not, I mean, a priori, it may not have a positive coefficient because so there is an example where you get the negative coefficient, even if you divide positive polynomial by another positive polynomial. And since it's an attractive conjecture, there have been many partial results. And I will mention some of breakthroughs. first, when some quiver has no oriented cycle. So if I start with some quiver, and then if I mutate properly, and if I get a acyclic quiver, then it would be relatively easier than the general case. So in this case, we have lots of tools from representation theory or geometry. Nakajima first proved for the bipartite acyclic cluster Algebras. But it turns out that positivity for bipartite seed actually implies positive for acyclic cluster Algebras. But that implication was made before real proof for the acyclic case by Kimura and Chu. And this was inspired by Hernandez and Leffler's work. And another breakthrough was Musker. In this case, they actually find the combinatorial explicit manifestly positive formula for cluster variables. And finally, we proved for the quiver case, and then another proof is given by Grosecki. I mean, they proved for a little more general case. But in this talk, I'm talking about just quivers. So, it's positive condition. Okay, so I'm going to give a sketch of this proof for both proofs. So actually, I want to compare these two proofs. Since actually they share many of the same characteristics. So for example, although our proof is a high school algebra, and then this proof is based on advanced mathematics, and then, but they share, nevertheless, both proofs have one has to have a very good control over those complicated looking rank 2 rational functions. We must have almost full control over. We have to know almost everything about those things. For induction. Grosecki conservation paper said that they can prove positivity by applying repeated applications. They said that, but they didn't really write every detail. But if they would write this induction, then that would be quite similar to ours. And actually, moreover, they have more on the same. So both the formulas for ranked cluster variables can be generalized to combinatorial formulas for basis elements in ranked cluster algebras. And moreover, both bases are equal. There are lots of good bases especially for ranked cluster algebras, like the triangulated basis and Kimura and Chin's another basis. There are lots of bases. They are not equal to each other, but these two bases are the same. And these two bases are different from the other bases. So essentially, they share many same characteristics. And moreover, it is expected that there is a natural bijection between both formulas. Okay. So, getting back to a proof, sketch of a proof. I take a sequence of mutations. I keep saying about rank 2 because a sequence of mutations will locally looks like wow. Keep mutating, and at some point we will repeat like in two variables. It may be very short, but anyway it occurs. Ranked subsequence, and of course you can mutate in another direction. So every sequence can be almost decomposed into rank 2 subsequence. This is where we have overlap between two rank 2 subsequences. Okay, so my setup is I need a mutation tree, so I need a bigger picture. I will start with some C, where the cluster variable I am interested in sits inside. Let's say this is X and T1. And if you are an expert in cluster algebras, you think this as a terminal seed, not an initial seed. I mutate in my way, not the standard way. So I have a bunch of rank 2 subsequences. then I'm going to use an induction on the number of ranked subsequences. I could go like this. I mean, these T1, T2, T6 are just named for the seeds. The indices just don't have any meaning. So my induction will assume that there is a positivity here. And yeah, there is a positivity for these Laurent polynomials. And then I will prove that the next, that there will be positivity for the next Z. And since I'm using the induction on the number of reactor sequences, I could get to this direction, but I could also get to this direction too. This is a JI reactor sequence, but I could take another reactor sequence along JK, and so on. Oh, by the way, this capital H is just a shortcut notation for the cluster. I could go this way, or side. From this branch, I could go up. So anyway, by induction on the number of ranked sequences, I already have positivity here and here, all the way up to here. And then I am interested in the next ranked subsequences. So the philosophy is suppose that we already know something about some positivity, especially something about these sequences where we are moving along K and J, and then the difference between here and here is only this ranked sequence. And since we have a completely explicit formula for ranked to cluster variables, we just substitute that formula into here, and then we will get the formula for there. Okay, so let me write possible form of the Laurent expression. So the cluster variable I'm interested in will be transformed like this. In the seed at T2, it will become like this. This is a Laurent polynomial anyway. So sometimes I have a negative exponent. Sometimes I have a positive exponent. I mean, the second sum will have a negative exponent positive, and the last sum will be positive exponent. these are rank polynomials in other variables. And our induction hypothesis is this is really the number of ranked subs. Okay, let me stick to F3 only for time's sake. F3 can be factored into G3 times some binomial expression. And we are assuming that it can be factored like this. It has some binomial that looks like a binomial in the mutation relation, and then another factor has positive coefficients. And then this third sum becomes the obstruction to the third sum is that we have negative exponent. So if we carry out the mutation, we will get negative power of some rational function, which is not pleasant. That will be hard to control. So we want to get rid of negative power. So if we have a factorization like this, then the third sum will be transformed like this. Notice that I changed the seed to get the opposite sign of the exponent. So I'm going to this way so that the mu k, and xk can be naturally become a denominator here. But this is a positive power of with the denominator. So since these are just positive power of cluster variables, we just apply rank to a positive formula, then they are still remain as a positive. So this is really monomial in J and K, Xj and Xk. So even if we mutate along JK direction, mu J, mu K, mu J, mu K, then still these are ranked cluster monomers. So still this is positive. So we still keep the positivity. And then now I'm running out of time. So anyway, this is our induction hypothesis. And then after that, mu I, mu J. Again, this will be expressed in the same way like this up there. The only difference between at the seed T2 and at the seed T6 is just that there is a rank 2 subsequence in between. So we apply. Since we have to control over factorization, we need to have a very, very explicit formula containing factorization. Which Schiffer and I developed in 2011, and this formula turns out to be the same as the Gross-Aitken-Kiel Conjectures ranked broken line formula. We still have the same, almost the same factorization. Factored in the same fashion like this. So that's how we get the positive hit. And it's just a brief sketch. So when just 1 minute. So yeah, so I keep saying that I keep comparing our proof and Gross-Aitken-Kiel consensus construction, and actually when I say basis, actually our ranked formula was generalized by Lee and Zelensky and me and this. So this is generalized to formula for rank 2 greedy basis, which consists of all positive indecomposable elements. And in their case, their databases, especially in rank, I mean they have databases for all rank, for certain cluster algebras satisfying certain nice properties. Well, so when they satisfy nice properties, they have databases. Especially rank 2 is nice enough, and it turns out that these two bases are equal. It's proved by some Gross, Ruppel, Harold, and Williams, and Stella. So, and since their constructions are the higher level of their construction, almost their combinatories are almost the same. So yeah, we can compare like this. Yeah, this is the end of my talk.